Hi, my name is Brian Caffo, and this is the Bayesian Inference lecture in the Statistical Inference Coursera class as part of our data science series. This class is co-taught by my collaborators Roger Pang and Jeff Leake, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So Bayesian analysis is named after a Presbyterian minister in the 1800s who was a mathematician and came up with Bayes' rule. At any rate, Thomas Bayes was his name, and I would suggest you look up things about Thomas Bayes. He was an interesting person. Any rate, so the way Bayesian statistics works is you have to have a prior. A prior is supposed to encapsulate prior knowledge about the parameter or be vague enough so that the likelihood kind of takes over. Oops, there's a little formatting there. So all inferences in Bayes analyses are performed on the posterior, the so-called posterior, which is the distribution of the parameter given the data. So in general, the way we think about it is that the posterior is the likelihood, which we covered in the last lecture, times the prior. Now it's a proportionate symbol there rather than a equal to symbol. There's a kind of normalization. So as long as we think of our posteriors in a relative sense, we're fine. So, going back to our lecture on diagnostic testing, the likelihood is the factor by which our prior beliefs are multiplied by to get our beliefs in the light of the data. Okay? So that's how Bayesian statistics works. So we're going to go through one particular instance of Bayesian statistics in the case of binomial data. So in binomial data, right, we have, let's say, a single binomial experiment where x is binomial n p. We only have one parameter, p. So we need some sort of density or something that encapsulates our uncertainty about p. Okay, and so we need a density on number, since p lies between 0 and 1, we need a density on the numbers between 0 and 1. And the beta distribution is a sort of default distribution for numbers that lie continuously between 0 and 1. So the beta density looks something like this, where this function right here is called the gamma function, which we don't need to worry so much about it. The beta, the kind of core of the beta function looks just a lot like the binomial, actually. It's p to the alpha minus 1, 1 minus p to the beta minus 1. But remember, in the beta density, the p is the random variable. Okay? Here p goes between 0 and 1. So the mean of the beta density, if we specify it in terms of these two parameters called alpha and beta, not to be confused with the type 1 and type 2 error rates, they're just parameters that we plug in. For alpha and beta greater than 0, the mean of the beta density is alpha over alpha plus beta, which notice has to be a number between 0 and 1, and then the variance of the beta distribution is that guy right there. The uniform density is the special case where alpha and beta is exactly 1. Okay, so let's actually explore the beta density, and the way we're going to do this is with the manipulate function, and I'm just going to create some values to plot, and then I'm going to manipulate over the two parameters that define the beta density, the alpha scale parameter and the beta, the alpha rate parameter and the beta rate parameter. Okay, so let's explore the Bayesian density using the manipulate function. So I'm going to create some p-values to explore, and then here's my beta density. Now its default value that I set it at was at 0 and 0. I'm sorry, at 1 and 1, which yields the uniform density, and it can go down to 0, right? As you can get it to look like that. So it can look like a kind of pushed up near 0, or you can make it look like that, right? Which is about 0.5. 0.5 is sort of a famous prior, and it looks like a U. Okay, let's go in the other direction. What if we were to make it kind of, oh, yeah, we can get interesting shapes like that. That's about 2 and 2. So that's this function that's basically p times 1 minus p, right? Maximized at 0.5. So if we make alpha and beta equal, we can make it symmetric and more concentrated in the middle, okay? And then as you make alpha and beta bigger and bigger, you can make it more concentrated, but you can also skew it toward the toward one side or the other. So so we can get it kind of skewed more towards higher values, or we can get it skewed more towards lower values by making beta bigger. So you see, you can get an awful lot of shapes, right? That's a very different shape than that one with the beta density. So play around with your alpha and your beta parameters and see all the different shapes that you can get. So it's a very kind of flexible prior, right? So if we have a prior, just to let you know, so if we have a prior like this, let's see, if we have a prior like this, then we're saying, yeah, we think for the most part the parameter is kind of like mostly around 0.5. If we have a prior like this, hang on, we're saying, yeah, we don't know. It's kind of equally like, roughly equally likely to be anywhere between there. In fact, we can make it exact constant. Maybe I can't. Yeah, well, I can't make it an exact constant given the step size I created, but we can make it an exact constant. It's just a horizontal line. Okay, so suppose that we chose the values of alpha and beta so that the beta prior is indicative of our degree of belief regarding p in the absence of data, or it's, a diffuse value like a uniform or something like that, okay? Then there's a lot of different ways to be a Bayesian. I'm kind of covering a very classic way of being a Bayesian. So then using the rule that the posterior equals the likelihood times the prior, and throwing out anything that doesn't depend on p, we have the likelihood part right here, okay? And we have the prior part right here, the beta density. Put them together and we get p to the x plus alpha minus 1, 1 minus p to the n minus x plus beta minus 1. Now remember, our data is fixed now, right? For Bayesian, we're looking at the distribution of the parameter given the data. So the p part is sort of the part that we're interested in. And notice if we look at this guy right here, it's just another beta density, only now the alpha parameter is x plus alpha, and the beta parameter is now n minus x plus beta. So the alpha parameter gets updated. So you can think of the alpha as sort of the a priori number of successes, and the beta parameter is the a priori number of failures. And then the alpha tilde, the posterior, is the posterior number of successes and the posterior number of failures. Notice, by the way, we cannot set alpha and beta a priori to 0 because that doesn't yield a valid density. You have to have them greater than 0. There's some interesting ways to think about what happens with the mean, for example, in this case. So the expected value now of the parameter given the data is alpha tilde over alpha tilde plus beta. The prior mean is alpha, so the expected value of p, the prior mean without considering the data was alpha over alpha plus beta. Okay? I should say expected value over the prior. Let me just write a little note there. Expected value over the prior. This is equal to that guy, right? And I can rewrite it like this. And then trust me or go through the arithmetic, you can write it out like that. And so look at what the form of this is. You can write it as x over n times this plus alpha over alpha plus beta times this, which is the MLE, p hat, times some proportion plus the prior mean times some proportion. So whenever you, and these two proportions add up to 1, pi and 1 minus pi clearly add up to 1. Whenever you take a times pi plus b times 1 minus pi, that's an average of the two numbers a and b. It just, if we take pi equal to a half, then it's a standard arithmetic average. But if we take pi equal to a different average, it sort of weights a more if pi is bigger than 0.5, and it weights b more if pi is less than 0.5. So this is a so-called average, it's a convex combination. So our posterior mean is an average between the MLE and the prior mean, where look at pi. So in this case, pi equals n over n plus alpha plus beta. If n is big, right, then this is going to be close to 1. If n gets really big, this is going to be close to 1. The data kind of wins out, right? As n goes to infinity, the data kind of wins out. On the other hand, 1 minus pi is alpha plus beta over n plus alpha plus beta. If n is small, then the pi is going to be close to 0. If n is small, pi is close to 0, right? And the prior kinds of wins out. And the prior mean is really governing things. That's an interesting way to think about what's the Bayesian calculations are accomplishing in this case. So I have this summarized right here. So the posterior mean is just a mixture of the MLE and the prior mean. And pi goes to 1 as n gets large. And for large n, the data swamps the prior. For small n, the prior mean dominates. So you can think of this as sort of generalizing how science should ideally work. As data becomes increasingly available, prior beliefs should matter less and less. With a prior that's degenerate at a value, if we make the variance of the beta distribution 0, then no about a data can overcome the prior. I would also note, this idea that you have a prior belief, you get data, and then you have a posterior belief. The Bayes calculation works really well in that if you then use that posterior as your new prior and collect new data, you would get a new posterior. That yields the same result as if you started with the same prior and just collected all the data at once without having updated your posterior in between. So it works out well that way. Okay, so let's just go through a quick example. Suppose that in a random sample of an at-risk population, 13 out of 20 subjects had hypertension. Estimate the prevalence of hypertension. So in this case, x is 13, n is 20. We're going to consider a uniform prior, which is alpha and beta equal to 1. Seen the formula on the previous slide. The posterior is p to the x plus alpha minus 1, 1 minus p to the n minus x plus beta minus 1. Alpha and beta are 1, so this works out to be p to the x, 1 minus p to the n minus x, which is the likelihood. So in this case, in the case of a uniform prior, the posterior is the likelihood. So consider the case where alpha and beta is 2. This prior is kind of humped around the 0.5. Then we wind up with something that is not the likelihood. We wind up with x plus 1, 1 minus p to the n minus x plus 1. The Jeffreys prior is a famous prior in this case, has some theoretical benefits. It puts alpha and beta as 0.5. Okay, so here I'm going to give you a way to explore the prior, the posterior, and the likelihood. I'm just going to create a plot, and then I'm going to use the manipulate function, and it's going to show as you change alpha and beta how it changes the prior and the posterior. Okay, so let's do that. Okay, here's my little workspace over here where I'm working on this lecture. I'm going to define my p-vals again. I don't think I have to. X is 13, n is 20. My plot is this function right there, and I'm going to do manipulate. All right, skerbam, it worked. Let's see. Okay, so the red is the prior, the green is the posterior, and the blue is the likelihood. Notice you can't see the blue in this case because remember when in this case, and I normalized everything so it has height 1, so they all fit on the same plot, right? When as alpha and beta go to 0, you wind up with likelihoods, the prior that heads off to infinity in the tail, and so I'm kind of truncating things and plotting it all so that its max height is 1. Okay, and so remember in this case the likelihood and the posterior are the same because the prior is just a uniform. So if you just multiply a function by 1, you get just the function back. Okay, let's take an instance. Okay, here. In fact, let's make it a little bit more apparent. Well, actually, here. Let's do this. Okay. Here's a nice flat prior. It's red is the flat prior, but it's humped towards 0.5. right? You can see that the blue is our likelihood. The green, it's more toward the likelihood, of course, because the prior is nice and flat, offering very little information. But it does pull the green a little bit away from the blue, and we could, we could make it much more that way by, let's see, there we go. There we go. There's a little nicer plot. Here I was quite certain, I was quite certain that P was around 0.1, right? It's fairly peaked at low values. My data says otherwise, 13 out of 20. What's 13 out of 20? 0.65. So I should have known that. So 0.65 is the MLE, so that's where the blue is over here. Get that back. So the green gets dragged in between the two, okay? And then I can make the, I could really drag it a lot more, okay? And then let's see, we can make it, so we can make it quite certain, that that it's 0.5, and then the green gets dragged more over. Let me change this a little bit so we can make ourselves a lot more certain. Okay, now the alpha can go way up there. Okay, look at that. Okay, now here I've done it where alpha and beta are at 100. We're extremely certain that P is 0.5. So our likelihood, which is blue, says, maybe not. Maybe it's more like 0.65. But because we're so certain in our prior, our posterior just sticks right around our prior. So anyway, that's how it works. Play around with the manipulate function. I love the manipulate function for stuff like this. Play around with it and show how your likelihood, prior, and posterior all combine together, or your prior and your likelihood combine together to create your posterior. So our posterior in the previous slides corresponds to our sort of representation of our beliefs in the light of the data, starting with the assumptions based on our prior. Or, if you're kind of a more modern Bayesian, it's a convenient way for exploring the likelihood, where we've set the priors to be some sensible values that represent kind of not too much concentrated knowledge about the parameter. And so that's nice, but you can't always give a plot. So we gave a likelihood interval, we gave a confidence interval. Why don't we give a Bayesian version of the same thing? So a Bayesian credible interval is just the Bayesian analog of a confidence interval. The one benefit, not the one, one of the many benefits of a Bayesian credible interval is they are 100% absolutely, positively the best in terms of interpretation. So 95% Bayesian credible interval, AB, would satisfy the posterior probability that the parameter just lies in the interval given the data is 0.95. Now, you could argue about what that probability corresponds to, whether it's a degree of belief or a frequency calculation or whatever. But people want to say the probability that the parameter is in the interval is 95%. In a frequency interval, that it doesn't mean anything because the parameter is not considered random in a frequency style analysis. So in a frequency style analysis, what you're saying is if I were to, the probability is kind of a calibrated unit to say, well, if I were to repeat this experiment over and over again, 95% of the intervals I got would contain the parameter I'm trying to estimate. The Bayesians can just say, yeah, the probability of the parameters in the interval is 95%. People want to do that, the Bayesians let them do that. Okay, so the best Bayesian interval, so there's a couple ways to get a Bayesian interval. If you have a posterior like this, you could just grab the points A and B so that maybe 2.5% lied in either tail, which in this case would be pretty easy. You could just use the Q beta function to get the beta quantiles, since we know the posterior is a beta itself. But there is a problem with that in the sense that, if kind of heights of this thing sort of correspond to better supported values, you really kind of want to chop it off and get the lines that correspond to it being chopped off. There's a small little annoying numerical problem of finding those points when you chop it off, but fortunately for us, someone did it, at least in this problem. And these sorts of intervals are called highest posterior density for kind of obvious reasons. You just want the point of the density, you chop off the density, and so you get all the points that are at that chopping off point and higher, but you calibrate it so that internal area is 95%. Okay, so let's get HPD intervals for this data set. It's easy. There's this binom package. Just do binom.bayes, 13 successes out of 20 trials. Type equals highest means highest probability, highest posterior density interval, and it gives you the alpha and the beta that you're using. I'm sorry, these are the updated. Okay, so 13 successes, 20 trials. 13.5 is the posterior shape, and this is posterior alpha, and 7.5 is the posterior beta, where it by default this uses the 0.5 alpha and beta for the prior, so the Jeffreys prior. It gives you the posterior mean, and then it gives you the lower and upper endpoints, and it tells you 95% interval. So, and yeah, the default prior is the Jeffreys prior. So I got another instance where I'm going to use the manipulate function to show you a HPD interval. Okay, let me try and get this. Okay, so I'm not going to just go through the code. I think at this point in the class, hopefully you guys are getting good at doing these sorts of things. I'm going to run the code, and here's my HPD interval. Right, here's the value of P1 and P2 that satisfy the interval, and what it's doing is chopping this off, and so I could set my confidence level at 87%. Notice the credible interval gets narrower as you set the level lower. So if you only want in this case a 61% credible interval, so that area in between these two red lines is 61%. Then it's going to be quite narrow. That makes a lot of sense. If someone were to put a gun to your head and said, the real value of P has to be between these two numbers, or I'm going to pull the trigger, but you get to set the credible level or the confidence level, obviously what you do is make that as big as possible, because but if you say I don't care so much about whether the interval contains it, well, then you get a nice narrow interval. Okay, but now you can, using this, you can see here's what the credible interval likes. You can change your prior values, and this will show you your posterior, and then you can, this red interval here is the HPD interval, right? So the where it connects with the horizontal axis are the two values of P that define the HPD interval.